In this Math 2203 video, we're going to take a look at linear independence. First off, we'll define what that means and see a couple examples of linear independence. And after that, we'll move into properties as well as geometric interpretation. To end off the video, we'll take a look at the Wronskian, which deals with linear independent functions. So let's define linear independence. Take a non-empty set S of vectors from our vector space. We're going to label those vectors v1 up to vn. What we're going to do is we're going to analyze the vector equation a1 v1 plus a2 v2 plus all the way up to an vn equals the zero vector. If this equation has only the trivial solution, that means that each one of those scalars ai are equal to 0, then we say that the set S is a linearly independent set. So our first example is we are going to show that these four matrices given here are not a linearly independent set of the vector space M22R. Our first step in this example is to set up the linear independence equation. So here it is with four vectors, a1, v1, a2, v2 up to a4, v4 equals the zero vector. And what we're going to do is we're going to combine all of these matrices together. So we get this 2 by 2 matrix is equal to the 2 by 2 zero matrix. So when we compare both of these matrices together, we compare the left-hand side entries with the right-hand side entries, we end up with this linear system. And if you remember from linear algebra 1, this is a homogeneous system. Now we're going to use the same kind of method that we did in the last video, and that is to solve this homogeneous system. We're going to take a look at that coefficient matrix A and figure out the determinant of that coefficient matrix. So if you haven't gone back to review cofactor expansion for 4 by 4 matrix, now might be a good time to do that. So what I've done for you is I've jotted down that 4 by 4 coefficient matrix A. And I want to refresh your memory on those equivalent statements once more. This is what we have. If determinant of A is not equal to 0, the homogeneous system is going to have a trivial solution. It means that our matrices are going to be independent. If determinant of A is equal to 0, we get that the homogeneous system does not have a trivial solution. It means that it has non-trivial or infinite solutions. And this means that the matrices are not going to be independent. So let's go ahead and calculate the determinant of this 4 by 4 matrix. What I'll do is I'll do a cofactor expansion across row number 1. So we'll get this number and we'll get this 3 by 3 determinant here, 0, 0, 1, 1, 1, 0, 0, 1, 1. And then when we move over here, we're going to get minus 1, and we're going to get the minor of that particular entry. So that's going to be this 1, 0, 1, 0, 1, 0, and 0, 1, 1. And then it's going to be up to you to evaluate those 3 by 3 determinants. Both of these 3 by 3 matrices give determinants equal to 1. So we will get 1 subtract 1 for a determinant of A that is equal to 0. So here's our final conclusion. Because the determinant of our coefficient matrix is equal to 0, we conclude that the four matrices that we started out with are not linearly independent. Another way of saying not linearly independent is saying linearly dependent. The next example we're going to take a look at is we're going to take a set from the real vector space C2. So here's our set S, and we're going to determine whether or not this set of two vectors is linearly independent in C2. So again, to start off this example, what we're going to do is we're going to start with our linear independence equation. And I'm going to fill in v1 and v2 as those vectors that were given in the question. Also, we have to consider the zero vector. So the zero vector of C2 is this vector here with 0 as both components. And what we're going to do is we're going to scalar multiply the a1 and the a2, these are real numbers, into these vectors. And then we're going to combine these two vectors over on the left-hand side. Now this equation that we have is going to lead us once again to a homogeneous system. The only difference is this time it's not going to be square, so we're not going to be able to solve this system using determinants. What I do want to explain to you is how I ended up with this homogeneous system. So, over here, I'm going to treat these as complex numbers. If I have a 0, that means that the real part and the imaginary part are both equal to 0. So this is the real part of the first component, and this is the imaginary part of the first component. Both of these values must be equal to 0. And if we do the same thing for the second component, here's the real piece, a1 is equal to 0. Here is the imaginary piece, negative a1 minus a2. So that's where we get this homogeneous system. And it should be pretty obvious to see that if we take a1, we already have a1 is equal to 0. And if we substitute that value into the first or the last equation, we get that a2 is also equal to 0. Okay, so overall we have that both a1 and a2 must be equal to 0. Because we solved that homogeneous system and we ended up with the trivial solution, a1 and a2 were both equal to 0, this tells us that that set S that we started with is a linearly independent set of the real vector space C2. The first property we'll take a look at regards the 0 vector. Theorem 1 says any set that contains the 0 vector must be linearly dependent. That means that any set containing the 0 vector is not linearly independent. The proof isn't too difficult. We just have to note that the 0 vector is equal to some scalar times the 0 vector. So we can create the following equation. We can write 0 is equal to k times 0, and then we just drop all of the other vectors in the set off. So what we get is we get that the 0 vector can be expressed as a linear combination of these other vectors where we don't have the trivial solution. Theorem number 2 deals with a set of two vectors. It says that if we have two vectors inside of a set, they're going to be linearly dependent if and only if the vectors are scalar multiples of each other. First, let's prove the forward direction. So we'll let our set S consist of two vectors, v1 and v2, and we're going to assume that this set is linearly dependent. That means at least one of these scalar numbers that comes in front of these vectors is non-zero. So if we were to write out the independence equation, we get this. If v1 and v2 are dependent, one of these numbers is not equal to 0. So let's pretend that a1 is non-zero. So what we have to do is we have to break this up into two cases. If a2 is 0, we get that a1, v1 is equal to the 0 vector. So v1 is really just the 0 vector. And we know from Theorem 1 that we're going to have a linearly dependent set. So we're going to consider the case where both of these are actually not equal to 0. If they're both not equal to 0, what we can do is we can move v2 over to the other side. So we'll have a1 v1 equals to negative a2 v2. And we can divide through by a1. So we could get that v1 is equal to negative a2 over a1 times the vector v2. So what we've shown is we've shown that v1 and v2 are in fact scalar multiples of each other. So here's the backward direction. We're going to assume that v1 and v2 are scalar multiples. And we're going to try to show that these two vectors would then form a linearly dependent set. So if they are multiples, we can write an equation like this. We could say that v1 is something times v2. We don't know what that something is. What we're going to do is we're going to move v2 back over to the left side. So we get v1 minus k v2 equal to the 0 vector. And so you can see from this equation here that the values in front of v1 and v2 are not trivial. They're not all equal to 0. So what we get is we get a linearly dependent set. Just to give you an idea of what Theorem 2 means geometrically, I'm going to keep it easy. I'm going to use the real vector space R2. So Theorem 2 says that every single dependent pair of vectors has to lie on the same line that passes through the origin. So for example, I've drawn a line here in yellow. I have a vector in blue that lies on that line, as well as a vector in red that lies on that line. Because these two vectors lie on the same line, they must be linearly dependent. That's what Theorem 2 is telling us. Most vector spaces, you can use all of the previous ideas in order to determine whether or not a set is independent or dependent. The only time we're going to run into a little bit of trouble using the other method is for the space of continuously differentiable functions. So for example, if we take Cn-1 from minus infinity to positive infinity, what do we do for independence and dependence then? Well, we have to use a special determinant, and it's called the Wronskian. What we're going to do is we're going to show that these three functions, 1, e to the x, and e to the 2x, form a linearly independent set of C2 minus infinity to positive infinity. So here's the guidelines to form that determinant called the Wronskian. What we're going to do is we're going to take those functions that are given to us in set S, we're going to place them in row 1 of our determinant. The second row of the determinant consists of all of the first derivatives of the functions in row 1. Then row 3 would consist of all the second derivatives of those functions. Row 4 would be the third derivatives, and so on. And we keep doing this until we have a determinant that is square. So let's form that Wronskian together. Usually to denote the Wronskian, you'll see textbooks or myself will use a capital W of x. That's just letting us know that we're going to be calculating the determinant of a 3 by 3 matrix over here. So what I'm going to do is I'm going to put those functions in row number 1. We had 1 e to the x and e to the 2x. So there's our row 1. In row 2, we're going to take the first derivatives of each of these functions individually. So the derivative of 1 is 0. The derivative of e to the x is e to the x. And the derivative of e to the 2x is 2e to the 2x. We still don't have a square determinant yet, so we need to fill in one more row. This is going to be the second derivative of these functions up here. Or you can think of it as the first derivative of this row number 2. So again, if we take the derivative of these functions here, we'll get 0, e to the x. If we take the derivative of this, we'll get 4, e to the 2x. So this is our Wronskian, and what we have to do is we have to calculate this determinant. You can do this determinant fairly quickly by cofactor expansion down column number 1. So what we'll get here is we'll get 1 times the corresponding minor. So I'm going to write out that minor here. It's e to the x, 2e to the 2x, e to the x, and 4e to the 2x. And then we just use the weave method on this little 2 by 2. And so the final answer that we're going to get is 2e to the power of 3x. If you calculate the Wronskian and you get it to be not identically equal to 0, then the set of functions that you started with is linearly independent. However, if you calculate the Wronskian and you do get that the Wronskian is identically equal to 0, then we can't conclude anything about that starting set that we started with. Of course, in our example, we had that the Wronskian was equal to 2e to the 3x, which is not identically equal to 0. So we're able to conclude that this set of functions, 1 e to the x, e to the 2x, is a linearly independent set in C2 minus infinity to positive infinity.